Hey class. I wanted to start off by talking about homework 2. If you haven't taken a look at it, you should. And if you have, I would be surprised if you weren't a little bit panicky or freaked out by the concept of having to complete it. That's okay. The problems I selected were from a little later in the semester last year. I thought they'd be more or less interchangeable, and I finally went back and read them, and I realized that maybe I haven't prepared you as much as I maybe should have before assigning these to you, but don't worry. So the one that I want to start off talking about is 1.3. It's the third order polynomial. I really want to emphasize taking advantage of your knowledge of programming and computer science to help you in some of these problems. So factorizing polynomials, factorizing, whichever is more correct, right? Factoring polynomials is a skill. You can use it, and once you find a root, then you can simplify the problem and reduce it until eventually you get something to quadratic. There is a formula for third order polynomials and another one for fourth order, and then there's a grand theorem that you can't have anything. You can't have a general solution for something fifth order or higher. But what I want to encourage you to do is one, realize that anytime I give you a polynomial and you have to factor it, it's going to have integer solutions, right? And then I want you to get in the habit of leveraging your newfound abilities to tackle these problems. So first, let me help you get started, right? So there's a pattern to all of these whenever you're looking at these linear, homogeneous, recurrence relations with constant coefficients, right, of order k or whatever that log explanation is, or whatever the title is for, right? So you have the problem of this form, right? And you want to get it into the characteristic polynomial. So you can follow a series of steps, or you can kind of jump to the chase. But essentially, you just replace a sub whatever value with r to that whatever power, right? So the subscript becomes the exponent. And if you're paying attention, then you're wondering, well, why? Well, that's kind of what they just developed, over however many decades, centuries, whatever it took them to get there, right? So it's not terribly intuitive why it necessarily works. So the fact that it only works in this very restricted case shows that there is some relationship, but beyond the fact that just massive trial and error was necessary in order to get this to work out, there isn't really this satisfying explanation for why there's this intimate relationship between these recurrence relations with constant coefficients and the homogeneous ones, and differential equations, which also follow kind of a similar pattern where the degree of the derivative or whatever turns into this. So it's again in these homogeneous problems or whatever. And so it's it would be fascinating if someone was able to come up with some clear explanation for what this relationship is. But for now, we're studying it and we're memorizing it because we know that it solves certain special cases. And in our case, because it's building up to the master theorem, which will tell us how to compute runtime complexity for recursive formulae, right? For recursive algorithms, and so that will help us to understand. So it's kind of easy to count runtime whenever you just have the one method and then you're kind of counting the loops and stuff like that. I'm like, okay, well, I have this many loops, and none of them are embedded in each other. So then it's, if I have 3 loops, and the arrays are of size n, then it's going to grow on the order of 3n. If the loops are all inside of each other, and so I'm iterating through 3 loops, one inside another, then it's going to be on the order of n cubed and stuff like that. So that's pretty straightforward. But what happens when we start breaking a problem down and recursively calling the same function over and over again? Like, that's kind of messy, right? And so we're building up to, using recursion and these principles from calculus. We're building up to some way to compute that to understand runtime complexity for recursive algorithms. But first, we got to solve the homogeneous case, right? And so okay. So this is for now, just accept it's how it's done, right? But if you want to find that deeper explanation for what that relationship is, that's fine. But you make that substitution, and then you move them all over to the same side, so you have it equal to 0, right? Like that familiar form for polynomials. And then so n is going to go off to infinity, right? Like it can count to whatever term it is. There's no limit to it. But we want our polynomial in some, like, its characteristic, right? So it doesn't really depend on which term we're looking at. It's characteristic of the recurrence relation, right? So in order to get rid of the n up here, we divide it by this lowest term, right? So we divide it by r to the n minus 3 in this case, right? And then we get something of the form r cubed plus 3r squared plus 3r plus 1 equals 0. Okay, so now we have a polynomial. It's third order. If I gave you a fifth order one, I just told you that there's no general solution. What am I expecting you to do? It's unreasonable or whatever. Okay, well, now let me show you a trick to kind of take advantage of these additional skills that you're developing, and to kind of encourage you to get in the habit of using your newfound tools as part of your extended tool set, right? So I'm sure you've learned how to factor polynomials at some point, and if you're a diligent student, then you probably forgot and replaced it with, pushed it out with some other newfound knowledge. That's fine. It's essentially long division, but with polynomials, and it's fine if if it divides evenly or whatever. But unlike with long division where remainders and improper fractions make sense or whatever, you can't really get that necessarily. Like it has to divide imperfectly for this. And so, other methods are typically used in order to find these roots. And so, in this case, and I guess in every other case, there's a simple trick. But so I'm going to show you what I'm encouraging you to do, and then I'll show you how to come up with like effective bounds on what I'm about to show you. So okay, let's jump to it. Okay, so here's the problem that that I gave you. It's not quite a nightmare, but it could be, right? Okay, so we go to our trusty console, and so I told you how to convert this to the characteristic polynomial, and that should be fairly familiar. So let's define our function, right? And you can kind of already see where I'm going with this due to the auto completion there, right? So we type in our characteristic function, so r cubed plus r plus 3r squared. Here, I'll keep them together so it's easier to see. Plus 3r plus 1, right? So that's it, right? We call f, we pass in some number, it spits out the result of this polynomial. Okay, so we're interested in cases where f of some value r is equal to 0, right? So we'll take a guess that all of the roots, so I'm telling you that I won't give you a problem unless it has integer roots, right? So we'll say, well, it looks, all of the coefficients are fairly small, so the roots are probably located between plus or minus 100, right? So let's create a loop. Okay, and we'll test for exactly what we're looking for, right? So our our iterator variable, right? Or we could call this r if we wanted, but it's a loop, and the loop uses an iterator. So that's our input for the function. And we want to test if that is equal to 0. Okay? And if it is, then I want to log it. So found a root, and then the value. Okay, so -1. So let's test that again. Do a sanity check. -1 spits out 0. And so, yeah, it looks like, that is it. And so the right. Okay. So whenever you have a polynomial, so it's a root of multiplicity 3 at -1. So r minus 1 cubed, right? Is really what we're looking at there. And so you can do other methods, right? You can come up with other reasonable approaches for that. But if you have it of this form, right, where, well, if this was like r to the 7 plus, something times r to the 5 plus something times r cubed plus r squared, and then there were no coefficients after that, then you would immediately factor out r squared. So there's a second order, or a root of degree 2 at 0, right? So you'd factor that out, and then you would deal with the rest of the polynomial. And so once you get to where that last term is a constant, right, something other than r or n or x, whatever variable it is that the function is defined with, then this will give you a hint as to where you need to look, like especially if you're guaranteed integer coefficients or integer roots. It'll tell you where to look, because this number is getting multiplied, right? Like if you have so if you have x plus a1 times x plus a2 and so forth, right? X plus an, right? Here, let me use a different variable so you don't get confused with that one. Right? So that's a j, if you can't read it, right? Then, on the far left, you have x to the j, right? Because, using the FOIL methods, first, outer, inner, last, or whatever, and then you just continue to do that until you multiply the whole thing, right? And then you have a bunch of junk in the middle, and then at the other end you have a1, 2, j, right? So this one is purely the first terms multiplied, however many times together, and then this last term, the one that I told you is just that trailing constant coefficient, right? Is just the last ones multiplied all together, right? So, so you have a root here, right, at x equals negative a1. So when x is equal to negative a1, well, this is 0 times some other junk, right? And then, x equals negative a2 here, would also give you another 0 for the polynomial, and so forth, right? And so what this tells you is that your roots will be factors of whatever this number is. So it might be positive, it might be negative, but if you factor it, then you can kind of limit the number of values that you have to test. So the fact that that trailing term was a 1 told us that that our factors had to all be 1, right? Like with the additional guarantee that I have promised to only give you roots at integer values, right? So our two possibilities were that all three roots were, so just considering that last term, right, that all three roots were, or the polynomial broke down to plus 1, like all three roots were positive 1, or that two of them were negative 1, and then the last one was 1, right? So so those were the possibilities. So we didn't have to check from negative 100 to positive 100, but I just wanted to show that, for the computer, it's not like I'm checking these by hand, right? I could tell the computer, well, check between negative 1,000,000 and a positive 1,000,000, and it would still complete, faster than I would check, 2 or 3 values. So, it's no skin off my back to have the computer check all of these values. So if you're only testing for integer values, it's really not that bad. So anyway, I just wanted to, encourage you that since, you're doing all of this work at home, and you're also trying to develop your skills as a developer, take advantage of it, and just if the opportunity presents itself for you to clobber one of these problems with some simple program, go for it. As was, we were able to do this in like 4 lines or something like that, right? So just look for opportunities to do that. Okay. And then the second problem, which I have thus far completely failed to prepare you for, but I will rectify right now. Okay, so the second problem. Why am I asking for this, right? Like, expansions or whatever. What are you even looking for, right? Okay, so this one is really not so bad, and I'll just kind of tell you what I'm looking for, right? So here B is some value, and we're generating a polynomial, right? That's why I used P instead of F or whatever, right? So the polynomial generator with base value, in this case base 16, will be something of this form. So what do you have to do? Okay, so first think about how we represent base 10 numbers, right? So the number 153 is 100 plus 50 plus 3, right? So hundreds plus tens plus ones, or 1 times 10 squared plus 5 times 10 to the 1 plus 3 times 10 to the 0, right? And so that's essentially what we're doing right here. And so I haven't given you a value. I want you to give the just the polynomial for it, right? So generate the polynomial. And it's a little confusing, but essentially all I'm asking you to do is replace the base b, or the base variable here, with the base value of 16, right? So you can represent numbers in base 16, or really any arbitrary positive integer base, using this, right? Or I guess base of larger than 1. So something in base 1 would essentially be like tally marks or whatever, but that's not terribly interesting. So we want at least binary or some greater base number, right? Okay, and so yeah, just replace b with 16. So then you get c sub k. So the kth coefficient is going to be 16. What you multiply 16 to the k, and then ck minus 1, 16 to the k minus 1, yada yada yada, and so forth, right? And then the restriction is that all of these coefficients, so in the way that we can't have, so we can have numbers larger than 10, but no column in our decimal representation will have a value larger than 9, right? So if we wanted, 1000, well, we would just say 1000, right? So instead of 10 times 10 squared, we would just promote it, and it would be 1 times 10 cubed, right? Does that make sense? So that same thing happens in binary, right? It's all ones and zeros. There are no twos in a binary representation. In octal, there are no eights. Right? And so in hex, there are no 16s. And what we're essentially saying is that every one of these coefficients, as we're building our base expansion, is bound between 0 and 15, or greater than or equal to 0, and definitely less than 16, right? So that's it. Just replace the b with 16, and that one's done. Okay. This is a limit, right? So show that it's asymptotically bounded above. So if you create a limit of g of n divided by f of n, show that the limit goes to 0, and in that sense, you're showing that it's bounded. Right? So, and then this one, so this one, my students at the end of the semester deemed it a little too hard to solve. So I definitely feel a little bad about leaving this in there. But you know what? I'll tell you. I'll show you the trick to it, and then I'll leave it to you to write it down or to track it. Okay, so. Yeah, my apologies, right? Okay, so this big O notation, right? Like we're showing that something is, it's bounded by, and I use the expression bounded below by, but it's like it's it's something whose worst case is no better than, right? So it's a little confusing in the notation, right? But the big O, you can say that it grows on the order of, or something like that. And so essentially what you're looking at whenever you use big O notation is just what is the largest term that's there, right? And so if you had something that looked like, 5 plus a squared is log base 2 cubed plus 5 million, right? So you just have some constant over here, and you have a bunch of junk. And you just look at him like, dude, I don't care about the specifics. Just tell me, what is this thing going to look like when, we go from a million users to a billion, or, from 1,000 to a million, or more likely from 1 to 10, right? So you look at this, and it's, again, calculus and limits and stuff like that. And you just say, okay, well, which one is the dominating term? What is the, not strictly speaking the principal part, right? Because it has more connotations or whatever. But what is the dominating term of this function? And so when you're dealing with the exasperated person and they just want the summary, like what does it grow on the order of? Well, then you just get rid of all the smaller terms and you only look at the biggest one. And in that case, in this example, we would say that it grows on the order of n to the 5, right? So what I'm asking you for is, if you're given some function something that grows on the order of log of n factorial, right? And so when would this come up, right? Okay, so the log here is assumed to be base 2. And let's say that you have Okay, so you have some binary tree, okay, and it has n factorial leaf nodes. So no more than n factorial, and no fewer. Right? So you want to know, like, where this comes in is what is the height of our tree. So if we start with some deranged input, and we want to make our way down to one of these specific leaf nodes where it gives us some magical solution at one of these leaf nodes, we want to know how many steps does it take to get down to that magical solution for our deranged input, right? So we know that the number of leaf nodes is n factorial, and we know that the number of steps is the height of this tree. Right? And so the height is given by log base 2 of the number of leaf nodes, which in this case is n factorial. Right? Okay, so that sounds like madness, right? The factorial function isn't, terribly friendly, right? Okay, well, let's review one basic property of logs, right? So the log of a times b is equal to the log of a plus the log of b, right? And that makes sense. So if you have right, so 4 times 2, right? If we want to know what the log of this is, right? It's the exponent, right? So right. So this is 8. 4 times 2 is 8. It's the same as 2 cubed. And the math checks out. If you break it up, if you follow this property, then you get that the exponent is, again, 3, which is what we would expect, right? So it gives us some way to relate multiplication using the log function, right, and change it into a summation. So okay, so now we have this. Which is n times n minus 1 times n minus 2, yada, 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 times 1. So this will be broken up into this summation, right? So log base 2 of n plus log base 2 of n minus 1, so forth, plus log base 2 of 1. Okay, so that is a starting point. So we now have something that's kind of workable, and so. But it's still, kind of a nightmare to get to big O notation, right? So like, there's got to be some other trick, right? And so you can scratch your head for a little bit and say, okay, well, somewhere between here and here, right? There's going to be a term that looks like this, right? So the log base 2 of n divided by 2. We would expect that to be halfway, right? So half of the elements are greater than or equal to this, and the other half of the elements are smaller than that, right? Or half of them are going to be greater than this, and the other half will be less than or equal to that. Okay, so then you have this, which is 0, this, which is 1, and then yada yada yada. You get this over here. Like, okay, well, I have some constants over here, and I have a variable over here, but really what I want is to get it kind of in terms of n. Is there some way I can count it? Well, luckily big O notation lets us kind of be a little bit rounded in this fact, right? So we just want to show that it grows on the order of. So we can't say anything definitively about this first half, but what we have over here, right, is that term by term, every one of these is larger than this value, right? And by count, we have half our elements over here, so n over 2 elements over here. Then we can't say anything about. We know that, the cost of, this isn't terribly expensive. We know for sure that it's bounded above by what's going on over here, right? So, in this case, it gets more and more costly to add items, and we can make definitive statements on this half, right? So we know that this function is bounded below if we just get rid of this, right? And we say, okay, well, it's more costly than what I'm going to say from here on out, right? So this is greater than if we multiply, if we simplify every one of these to the element that it's bounded below by, which is log 2 of n over 2, right? Because every one of these elements is more expensive, right? Just look, the inputs, log is strictly increasing as n increases, right? And so these all get more and more expensive, right? And there's n over 2 of them. So then we can say that whatever it is, whatever log 2 of n factorial is, it's definitely larger than if we round this off to 0 and we round this half term by term down to something where they're all bigger than, right? Which is the largest element of the set that we just threw away. Right. Okay. Okay. So then this, right, we can now make our big O notation, right, on what we're bounded below by. Once you get to big O, you only look at the largest terms again, right? Like we'd kind of already discussed that, right? So this So we say that this is on the order of, well, I'll get rid of the constant coefficient, right? Because we only care about the value in. Okay. So in, and then again we have another constant coefficient that we don't really care about. So we did it. That was it, right? Like, so the trick is to break it up into, like you expand it, right? You take a look at the fact that you're multiplying. You use the property that multiplication within the log is addition once you separate the terms, right? And then you use this bounding fact, right? So each one of these terms on the larger half is bounded below by n over 2, and there's exactly half the set is larger than this value. And then so we're rounding down basically, right? Because we want to say that it's bounded below by something. So we round this part down to log, term by term, to log 2 of n over 2, and there's n over 2 of those rounded terms. And then we round this half, term by term, down to the smallest element, which is 0, right? And so we have this lower bound on the number of steps, the number of operations that binary tree that we were looking at with n factorial leaf nodes. So we have some lower bound on the minimum height for that tree. And so the rabbit in the hat of all of this, like what we can pull out, is that we can say, okay, so if you have something that must, so if you look at that as a computer program, and each one of those branches as a branch point in the computer program, so something that's determined by an if statement, and the leaf nodes are all of the possible final states, then for something like a sorting algorithm where you have n factorial possible arrangements of an array of size n, right? So that's how many permutations you can have on the input. And then the tree represents all of the number of choices that it has to make in terms of whether or not to swap two elements in order to get to the sorted output, right? So there is a specific permutation operation that'll take a derangement of elements and put it into a restored sorted order, and that's what that tree that I drew earlier represents. And so the number of those final states is n factorial because it's the number of permutations, right? So that's already well known. And so this argument, shows it uses tree height, this binary tree, decision trees, to tell you that in a sorting algorithm can do no better than this, basically, in terms of deterministically guaranteeing a solution to the sorting problem. And so if you have something that grows on the order of n log n, then that's as good as you can get, because that's, this problem is bounded below by something with a worst case runtime of that. So if you can't do better than that and you've already achieved it, then you've essentially got something that's as good as can be. And so merge sort is in that sense, essentially as good as can be in terms of sorting. And so, but that's in the worst case, right? So there are ways to beat it, in terms of best case, but but in order to get that advantage, then you have to also risk something, right? So if you're solving for certain cases where like only a few elements are permuted or something like that, then you might be able to optimize it. But then in the worst case, like you will push your worst case back. So again, in that sense, merge sort is essentially as good of an algorithm as you could hope for in terms of sorting. And so that's the proof. This is essentially all that you'll need to write. Like, So this would go down here on the line below, right? And then that's 2.3, right? And we've already discussed the other one. So you should have everything you need to make headway on your on homework 2. And then yeah, okay. So we can finally jump into class, right? Okay, so. Okay, yeah, so we discussed characteristic roots and characteristic polynomials, and then what to do if the characteristic polynomial is of degree k instead of degree 2. What to do if our degree k polynomial has multiplicities greater than 1, right? So all of this, this additional information and these confusing indices is basically saying what you would expect it to say, that you find all of the roots, and then each time you have a root that repeats, then for each repeat, so each time the root extends beyond 1, you tack on an n, right? And you get another new coefficient, and then you have to solve the system of equations and so forth. So this is if you have to solve it like by algorithm. If you have some recursive formula that is insane, right? and you have to deal with some super high order one or whatever, and you're not solving it by hand, then yeah, you would end up testing for all of these additional cases. But no one expects you to factor some characteristic polynomial that's I wouldn't expect anything greater than quadratic by hand, but because you have your computer and I've given you these heads, right, I might ask you for something up to degree 3 or 4 or whatever. But again, it'll always be, when I give it to you, it'll always be an integer, and then you can use those additional tricks. But this is just the general formula, and this is given for academic purposes. But no undergraduate is going to encounter something like this. And I would struggle to imagine any really high degree recursive formula that I'm aware of. I mean, you can come up with anything, right? So it's not like it can't exist. It's just hard for me to come up with something that has some meaning or whatever. But this formula is included to show that, yeah, there is a general solution to the general case of some linear homogeneous recursive relationship with constant coefficients of degree k. Yada, yada, yada. Okay. All right, so what happens if we have some extra junk, right? So we have the homogeneous case, and then we have something that just sits out there, and it depends only on n. Okay, so then we split it up. So we look at the recursive, like the associated homogeneous recursive relation, right? And we find a solution for that, and then we deal with the particular case of f of n, right? And so so here's the theorem. If you're given something of this format, then the solution, and this is again similar to differential equations for whatever reason, there must be some intimate relationship. I mean, obviously between polynomials and them, but between recursive relations and homogeneous differential equations of constant coefficient. And so anyway, but then you have the particular solution and the homogeneous solution. And so the homogeneous is the solution to this, right? So it's what we were just discussing, it's what we were looking at the homework or whatever. And then the particular case is once you account for for this Fn function, right? And so, okay, so now we have a theorem for what the particular solution looks like based on what f of n looks like. Okay, so f of n deals explicitly with n, and so there's some some constant s raised to the exponent n, right? And it's optionally multiplied by some polynomial. Or I guess I shouldn't say optionally, because if the polynomial is 1, right, that's still a polynomial, but you're not multiplying by 0, right? Because if you're multiplying by 0, then f of n would be 0, and we would just have the associated homogeneous recurrence relation, right? So so we break it up, right? There's this polynomial times s to the n, where s is some real number, and then these are coefficients, right? It's just a polynomial, don't be confused. Okay, and so if s is a root, right? Or sorry, if s is not a root of the characteristic equation, then we don't have to do that weird thing where we multiply by n times the to the multiplicity, right? So we just have something of this form. If it is a root, then how we were tacking on n to the multiplicity minus 1 or whatever, right? So if the root was repeated, so if it was squared at that particular 0, or the 0 was degree 2, then we would have this term, and then we would have some other coefficient times n times r to the n. Right? And so, well, n is n to the multiplicity minus 1, right? N to the m minus 1, where m is 2, so it's n to the 1, but it's 1 less than the multiplicity. And so the extension, right, like if we have this non-homogeneous function and s is a root, then we get to carry on, we get to add that one more n over here, right? And that's on top of this polynomial that will be of the same form, of the same degree as the particular function, right? The non-homogeneous function, right? So we have something here, and it's going to have the same degree polynomial, right? So we have s to the n, which we have to deal with, right? But we have this polynomial, right? And the one that appears in the particular solution is going to have the same degree. And then you're asking, well, what are these coefficients or whatever? Well, you have to solve that, right? Like you're using these theorems to create this system of equations, and you need enough reference points essentially in the recursive formula to solve this system of equations. And so it's the same as it's been throughout algebra for all time, right? So if you have a dozen unknown variables, so the coefficients here combined with the coefficients to the homogeneous function, so all of these alphas and whatever, if all of the stuff you don't know that isn't in or whatever, that isn't the input variable, adds up to a dozen, then you need a dozen base cases or whatever. So you need A0 through A11 or whatever, so that you can create this system of equations that will allow you to solve it. And then and then you deal with that nightmare when you get to it, once you've created the situation or whatever. But that's essentially how you solve it, right? Like these are just unknown coefficients at that point. And so then you'd solve it just like any other linear system. Okay, so so as an example, like, well, what did we just say, right? Okay, so consider this recursive relationship. So this part is familiar. This is the linear homogeneous with constant coefficients, right? And then this is the non-homogeneous function. So we want to know, like, what form does it take, right? What form does the particular solution take? And so we use that theorem that we just covered to go over that. So if f of n equals 3 to the n, what does the particular solution look like? If it's n times 3 to the n, if it's n squared times 2 to the n, or if it's n squared plus 1 times 3 to the n, what does it look like? Okay, so f of n is in this format, right? And so we have to like simplify. Like, okay, so let's plug in our numbers. So here f of n is 3 to the n. So this polynomial is just b0, and b0 is itself 1, and s is equal to 3. So we've managed to make our substitutions. We figured out what it looks like how it relates to this general form of the non-homogeneous function. Right? Then so forth. Here s is again 3, here s is 2, right, because it's 2 to the n, and here s is 3. And then we have some other junk in these leading terms, which we'll deal with in a second, right? Okay, so the first question we have to know, right, because going back to the theorem, it says if s is not a root, then use this form, and if s is a root, then use this form, right? So is s a root? Well, we have to solve the homogeneous recurrence relation first. So as I showed earlier, right, we replace a with r, and we move the subscript to the superscript, right, because we're acting on faith that works, and it does in this case, right? Like we've explained that, right? Okay. And so then we move everything to the left-hand side, and then we divide by the smallest term, right? And so you can kind of just jump to the chase if you know that this eventually becomes this, but I want to show like how we keep coming back to the characteristic equation. Right? So our characteristic equation is r squared minus 6r plus 9 equals 0. So we need to factor that, and it's r minus 3 squared, right? So our root is 3, and it has multiplicity 2. And so, yes, in the case that s is equal to 3, it is one of our roots. So we have f of n times some polynomial, or is equal to some polynomial times s to the n, right? And so if it's just a polynomial over here, then s is 1, right? Just want to mention that is a possibility. But, okay, so the polynomial as this form, or b sub whatever are the coefficients for the polynomial, times s to the n. So we don't have any other terms on the left-hand side, so it's just a constant. That constant turns out to be 1, and s, because it's of this form, right, s to the n, s turns out to be 3. 3 is one of our roots, okay? It has multiplicity m equals 2, right? So then, going back to the formula, right? So when s is a root of the characteristic equation, we use this formula, right? So we come back down here, right? We use that formula, okay? And so we know that the degree of the particular solution, the polynomial in the particular solution, matches the degree of the polynomial for the non-homogeneous function, right? So it's degree 0, it's just a constant, right? So again, we have just some constant, right? So this polynomial, we don't have any higher order terms than this constant p0. So then we have this one unknown that we have to deal with for the particular solution, right? We know that m, right, because s was in the solution, right? M is equal to 2, okay? And then, so we can plug that in, and we have that this becomes n squared, this becomes p0, right? And then s was 3, right? We'd already established that. So then this is the form for the particular solution. Okay, so what happens if our non-homogeneous function is of this form, right? So this is a polynomial of degree 1. It's just n, right? It doesn't have all of the fanciness of a polynomial of what it could, but again, we're matching terms here, right? So we have that this polynomial, this p of n, becomes b1 n plus b0, right? In this case, b0 happens to be 0, and b1 happens to be 1, right? But we show that it's of that form, and that tells us how many unknowns we'll have whenever we get to the solution. Again, s is whatever s to the n, right? So s happens to be 3. Again, 3 is our root. It has multiplicity 2. So our solution will have this form. Okay, and again, the polynomial in the solution is going to look a lot like the polynomial for the non-homogeneous function. So this, okay, reduces to this, which looks a little bit like this, right? It's a degree 1 polynomial. Okay, S was a solution, so n to the m becomes n to the multiplicity of s, which was 2. Okay, and then s gets replaced by s, right? So this s to the n becomes 3 to the n, right? And so now this is the form for our solution. Okay, and so what happens if we have n squared times 2 to the n as our non-homogeneous function? Okay, so this is the non-homogeneous function, so this form, polynomial times s to the n. So the polynomial is degree 2, so coefficient times n squared plus coefficient times n plus coefficient times n to the 0 if you want, or just the coefficient. And then all that times s to the n. And so this simplifies down to n squared. This, in this case, our s is 2. Okay. So 2 is not one of our roots, so we don't need that n to the m at the beginning. And we just have polynomial times s to the n. Well, polynomial is again degree 2 because the input was degree 2. And then s was the value 2. So our particular solution looks like this. Okay. And so what happens if our input looks like this? Okay, so degree 2 times 3 to the n. So degree 2 polynomial times s to the n, or degree 2 polynomial times 3 to the n. 3 is a root, multiplicity 2. So because it's a root, we use this form. N to the multiplicity is that. Polynomial reduces to degree 2 polynomial because, again, the non-homogeneous function had a degree 2 polynomial. And then s was determined to be the value 3, right? 3 to the n, so 3 to the n over here. Okay, so that's how to deal with the non-homogeneous terms in the linear recurrence relation with non-homogeneous, or linear non-homogeneous recurrence relation with constant coefficients. Okay. So now we move ahead and we can discuss divide and conquer. So we've kind of already seen divide and conquer in merge sort and binary search, where we have this recursive function and we're reducing the set that we're working against with each recursive call so that we can simplify it. And so divide and conquer algorithms all have, they all look something like this. So we break the problem up into A subproblems, right, where the array size, or the collection that we're working against, is the original size divided by B with each recursive call, right? And so that relationship is the original array size is equal to A times B. So in the case of merge sort, we're breaking the problem up into two sets, right? Where the left set and the right set, and then the size of each set was n over 2, right? Yeah. So that 2 times times n over 2 was n, right? Yeah. Okay. So so the complexity of it, or the recurrence relation, looks something like this. So we've broken it up into this many problems, and we'll have to solve those problems, passing in a smaller set, right? And then there's some additional number of operations that are performed. And so in this case, we were testing, like in the case of binary search, we were testing to see whether the value was in was less than the midpoint, right? And then additionally, we were testing whether or not the minimum item index, or the min index, was less than or different than the max index. And so if you've already tested everything, if the minimum, if the left bookend has met the right bookend and you haven't found your item, then you're not going to find your item, basically. So this turned into a constant number of tests, right? So, but there's the potential that instead of performing these two comparisons, right, like is the index, or is the item I'm searching for less than the value that's in the middle of this array, it could be a loop where you're looping over the size of the input, like you're performing some loop action or whatever. So that's why it's a function that depends on n. So it might be a constant, but if you're looping or doing some other action, then there's potential that that this additional term, this non-homogeneous term, is linear or the non-constant, right? So linear, quadratic, superlinear, something like that. So we give the generic definition. Okay. Right, so the example here is in the case of binary search, and so each time we check to see, so we break the array in half and we check to see is search item less than the midpoint, and then is min item less than the max item, right? And so that's how we get g of n equals 2, and so our representation for the runtime and how we split up our representation for the recurrence relation takes the form of this, right? So it's a constant, and in this case a is equal to 1. So we're splitting it into subproblems, but we split it, because it's search, we split it into one subproblem. So if we identify that the item we're looking for is in the left half of the array, well, we never go back and check the right half of the array. So even though we're splitting it up into two, a is the number of subproblems, right? And so a equals 1. Oh, I guess I shouldn't have put that then, because we're splitting it up into 2, right? But 1 times 2 is not equal to n, right? So so this is, ignore that, right? Those, if you have to exhaust the list, like in merge sort or something like that. But even then, probably still shouldn't have put that. I will get rid of it at some point, right? But okay, so a does not have to equal n divided by b, right? Like, yeah, that was incorrect. So a is strictly the number of subproblems. So in the case of search, we're only looking once, right? We're only looking in one half, but we cut the problem in half each time. So we recursively call our function, and the size of the collection that we have to look at is half the size. And then with each pass, we perform 2 tests, right? Is search item less than the midpoint, and is min item less than the max item? Right? So this is the form for our recursive relation for binary search. Okay, and so merge sort also has a recursive relation. And so here, when we sort, we have 2 subproblems, right? So we merge both the left and the right half. So even though we split it in half, and we call merge, we are doing it twice. We're dealing with it twice. And then the non-homogeneous term is linear, because whenever we put our 2 arrays back together, so we break it down, and then we're guaranteed sorted arrays once we get down to singletons, right? Once we get down to arrays of just a single item. And then with each step, each time we merge back up, we're guaranteed that the output of that merge operation is itself sorted. But in order to merge it, we have to go through both elements, or both arrays, right? So we just take whichever item is next smallest when we're sorting in ascending order. from the two arrays. Like we compare the next item in each array and we pluck that item out, and then we have to go back and fill it in with all of the remaining items, all of the leftover items. So one of those arrays will be exhausted before the other, and then when that happens, we go back through and we pull in all the other elements. And so there's in operations that take place there, right? So that's where this in comes from. So the recursive formula for merge sort looks like this, right? So two subproblems, right? And then when we recursively call merge, we're dealing with half of the set each time, right? So both for the left half and the right half. And then whenever we merge, there's in operations or something on the order of in operations that take place. So this is the recursive relation for merge sort. Okay. So the assumption, let f be an increasing function that satisfies the recurrence relation. So all of your programs, none of your programs are going to get faster with the larger the input set, right? Like essentially everything we do as programmers, we satisfy this condition that it's an increasing function. So more input means more work, not less, right? So so f of n is of this form, right, where c is some constant. Right, so we're not having to loop through like in merge where we're merging the operations later. So we have something here, subproblems times some recursively called function plus some constant number of operations. Right. Then f of n is on the order of n to the log base b of a if a is greater than 1, or it's of the order log n if a is equal to 1. Yeah, so our binary search was log n, right, log base 2 of n, where a was 1. And so this theorem says that that's the general case where if it's constant over here, then you basically throw that away and it's fully determined by what happens over here, right? And so if a is 1, then you have something that's on par with binary search. And if a is greater than 1, then you have something that grows on the order of n to some exponent, where the exponent is the log of a base b. Right? So in the case of merge, well, we can't use merge, right, because we had n over here. But yeah, then you would get n to some exponent that is a log. And then it says, okay, well, furthermore, if a is greater than 1 and n is equal to b to the k, with k some positive integer, then f of n takes on this form, right? So we've substituted this, right? And then we have these constants. And then the constants have this form, right? So I think really this is the interesting part of the theorem, but this gives you an alternate expression for it. So, okay. So then the master theorem, like, okay, well, what about the general case? So this deals with the case of a constant term where you don't have to loop through the results or the output of your recursive function like we do in merge, where we have a loop of length n, basically, or really 3 loops that add up to a length of n. And so the master theorem says, okay, well, in that general case where you have a subproblems and you're recursively calling the function with an input the size of n divided by b, and then you have an additional number of operations, c times n to the d, right? Where n to the d is the number of, right? So n to the 1 would be 1 loop, n squared would be an embedded loop, and then c is just the number of times you have that atrocious number of loops, right? So this is just a general form, right? But okay, so whenever n is equal to b to the k, right? So in this case, it's just easier to make these statements. Like in this case, if we're dividing the problem in two, right? Then this just says that n is some power of 2, so we can make some definitive statement. And so, but this would be true even if this wasn't the case, right? Just as long as, yeah, like it's essentially exactly true, or as close to exactly true as can be, whenever it's some power of b, right? Or when b is 2, then it's some power of 2. But like in general, I would expect these big O representations to hold. Okay, so then we have at least one subproblem, right? So in the case of search, we had just one subproblem. In the case of merge, we had 2 subproblems. And b is an integer greater than 1, right? So otherwise it's not divide and conquer, we're just recursively calling something over and over again. So this assumption is saying, well, and you don't have some Stack Overflow scenario where you just recursively call the same function with the same input over and over again, right? You are actually dividing it. And then C and D are real numbers, with C and D with C positive and D non-negative, right? Yeah. So that this term doesn't vanish as n gets larger. And so these are just essentially saying so that the function behaves as you would expect a recursive function to behave, right? Then if you get it into this form, then f of n grows on the order of n to the d whenever a is less than b to the d, right? It grows on the order of n to the d log n if a is equal to b to the d. So in this case, for merge sort, d was 1, right? So this says that merge sort was n log n, right? This is just another way of observing that. Or it grows n to the log base b of a if a is greater than b to the d. Okay. So okay, that's the master theorem. You can use it to directly analyze the runtimes, or the runtime complexity for your recursive algorithms. And so I think it's pretty cool that they were able to derive that. And so yeah, so the last example was returning to the merge sort, right? We have a merge sort with a recursive definition like this. So here A is 2, B is 2, C was 1, right? And D was 1. And so in that case, A was equal to 2 to the 1, right? And so we can say that merge sort is on the order of n log n, right? And then we use the decision tree argument at the beginning of this lecture to show another proof that not only is merge sort on the order of n log n, right? So this is computing how long merge sort takes, but we've shown that you can't resolve some permutation on a set of n elements in faster than n log n. And then we'll come back to the decision tree argument for a future proof. Okay, and so we'll come back and we'll do inclusion and exclusion next class, and we'll do relations, and we won't go further than relations in which is chapter 9 for the exam. Yeah, we'll just save graphs and trees for later, for future fun. Okay. All right. Yeah, that's great. I hope you all have a really good weekend. Let me know if you have any problems with the homework. I feel like we went over it a fair amount. But still, if you have any questions, let me know, or if you're running into any other trouble and something about this class is making you panic, or there's something that you need clarification on, we can discuss that too. So, okay, have a great weekend. Bye.